Hello students, in this video we are going to talk about fundamental theorem of linear systems. Sorry, let me write it properly. Fundamental theorem for linear systems. Okay, systems. So essentially, you see, we talked about the linear system, right? Variable coefficient. So we know that if we are looking at this problem, x prime equals to at times x, okay, x at the point 0 is x naught, then the problem has a unique solution. Problem admits an unique solution, and how is what is the solution here? It is given by x of t is the fundamental matrix phi of t times a constant which is a n cross 1 constant. Okay, sorry, this initial data is given, right? So it is nothing but phi inverse of 0 times x naught, right? Phi is the fundamental matrix, mental matrix. Okay, now the point is this is okay, but the thing is, for real life calculations it is not a very feasible option. So what we do is this, and this is why we talked about matrix exponential in the first place in the last video. Okay, so what we do is this. See, let's say so as a motivation, let's look at some motivation. So let's look at this problem. See, x prime equals to ax, let's say, yeah, and x0 equals to x naught. Yeah, you can easily check that xt equals to x naught times e power at, okay, is a solution, is the only solution, right? Only solution. A is in R, right? A is in R given. Okay, xt is the only solution. Now the thing is this, from here we can actually motivate ourselves that what should be. So now the question is can one find similar results for x prime equals to ax, x at the point 0 is x naught. Okay, I am writing 0, you can take it to be t naught, no problem. Okay, now here you see, please remark what I am going to do now. Okay, whatever follows in this video is only valid for a constant coefficient system. Okay, constant coefficient system. Clear? Okay, see this thing, this actually holds for the fundamental matrix solution, that actually holds for variable coefficient, no issue there. But the thing is, we expect that, let's say the variable coefficient becomes a constant coefficient, we can actually say more, right? Okay, we can see much more details. So that's what we are trying to do here. So let's say you have a constant coefficient problem, x prime equals to x, x0 equals to x naught. Let's call that as star. We want to find the solution. Okay, from the earlier thing, motivation, we can say that this is the thing, aim. You see, you can actually see, you can think of it like this, that e power at times x naught should solve star. You see, here e power at times x naught is a solution of this problem, right? Now if you are making it to be an n cross n system, then for that system e power at times x naught has to be the solution. You have to write it like this, because e power at is an n cross n matrix and this is an n cross 1 vector, right? So then makes sense. You cannot write x naught times e power at. Please remember that. You cannot write x naught times e power at. Yeah, okay, so please remember this part. Clear? Now you see, the thing is, xt equals to e power at times x naught should be the solution, right? That's what we can expect from this particular thing. Okay, so we are going to do that part. Okay, right? So this is the main aim hour. Okay, so let's look at a lemma first. Lemma. Let A A be a n cross n matrix, be a n cross n matrix. Okay, then we want to talk about the derivative of e power at. Yeah, so then d dt of e power at, what happens here? Okay, now from one variable you do realize it should be this should look like this, right? E power at. It should look like this, yes, and actually it does. Okay, so you don't have to worry about it. Okay, but the thing is, we of course need a proof of that. So let's look at a proof. Okay, so d dt of e power at, clear, is nothing but, this is our usual definition, limit h tends to 0, e power a t plus h minus e power at by h, right? So this is nothing but limit h tends to 0, e power at, okay, e power ah minus identity, you can write it like this, right, by h, clear? So this is nothing but e power at limit h tends to 0. I can take the e power at outside because it does not depend on h. So limit h tends to 0, e power ah. What is e power ah? It is nothing but minus identity. It is nothing but 1 by h. Okay, a plus a square h by 2 factorial plus, so 1 by h it will get cancelled. I am not moving this thing. Okay. Now this is nothing but, what happens? This is nothing but e power at times a, right? Okay, which is again, I mean this actually you can see that this actually commutes, so you can write it as a e power at. Clear? So we have our result. Okay, see the last equality which we are doing. So basically e power at converges uniformly. Okay, so that is why you can change the the two limits essentially. Okay, fine. I did miss something, no? I have to miss something. Limit h tends to 0. What is the k? Okay, fine. Yeah, this is okay. So right. So now we talk about the fundamental theorem. Okay, so theorem. So let A be a n cross n matrix. Okay, then given x naught in Rn, okay, the initial value problem, x prime equals to x 0 equals to x naught. So please remember this is a constant coefficient. Okay, admits an unique solution. What is the unique solution? Given by x of t is e power at times x naught. Okay, this is what you see. We were expecting this, right? So this theorem actually says that you have a unique solution. The unique solution is guaranteed by Picard's existence and uniqueness, and you actually say that there is a unique solution which is given like this. Clear? Okay, so how do you prove something like this? See, proof. If xt is nothing but e power at times x naught, okay, that will imply x prime of t is d dt of e power at times x naught. Okay, see, x naught does not independent of t, right? So we can, and so d dt of e power at, we know that it is a e power at times x naught. Okay, right? So you see, and e power at times x naught is nothing but xt. So this is a times x of t. Clear? So x prime t equals to a times xt. So xt satisfies the equation for all t in R. Okay, so xt given by e to the power at times x naught satisfies the equation for all t in R. Also, x of 0 is nothing but identity times x naught, e to the power a0, which is identity times x naught, which is nothing but x naught, right? Okay, so therefore, okay, see, the thing is, we have to show that, see, what we showed is xt equals to e to the power at x naught satisfies the equation. Yes. Now the thing is this: how do you show this is the only solution? Of course, you can use directly Picard's theorem, and you can say that this has to be the only solution. There is no other way. Without Picard's theorem, also you can prove. Let's just look at that proof. Okay. So what you do is you define y of t to be e to the power minus at times xt. You see, similar sort of thing we did it in the last video also, if you remember. Okay, y of t equals to e to the power at minus at times for xt. Okay, then what is y prime of t? Y prime of t is nothing but minus a times e power minus at x of t plus e to the power minus at x prime of t. Clear? So this is nothing but minus a e to the power minus at xt, and what is x prime of t? It is nothing but a of x, right? So e to the power minus at a of x of t. Now a and e power minus at, they actually commutes. Okay, so these two commutes, this one and this one commutes with each other. So basically we can write this is essentially 0, right? That will imply y of t is nothing but constant. Okay, yt is constant, and what is y at the point 0? This is nothing but x of 0, which is x naught. Okay, so if this is x naught, then what happens is that will imply y of t is always x naught, right? X naught for all t in R. Yeah, and then we can actually say what is y of t? It is x of t then is nothing but e to the power at times x naught. Okay, so this is proved. So this holds for all t in R. Now, so what we understood here is this. See, if you have a constant coefficient equation, at least homogeneous constant coefficient equation, what we have is you have a unique solution given by e to the power at times x naught, and that solution is valid for all of R. Okay, all of R. See, the thing is, here you may ask, why don't we use Picard? You can use Picard for the uniqueness thing, but the thing is, that is not guaranteeing that you can have a solution for all R. It only guarantees in a small neighborhood of 0. Okay, but here you can actually, using this proof, you can actually say this works for all R. Okay, so let's look at a simple example. Okay, so let's say that we have this problem: x prime equals to minus 2 minus 1 1 minus 2 x. Okay, and x at the point 0 is a vector given by 1 and 0. Okay, now I want to find out what the solution is. So the solution x of t, what do we know? We know this is at times x naught. Okay, so you just have to calculate e power at and you are done. Okay, and what is e power at? You see, this is in this form. If you remember, we did one problem, right? This problem, you see, a minus b, b a. Yes, in this form, e power a we calculated, which is looks like e power a cosine b minus sine b, sine b cosine b. Okay, so we can use this property here. So since e power at, what is e power at? Let's just write it down. We are just I'm just writing it directly. Okay, I am not calculating anything, writing it directly. It's cosine t minus sine t, sine t, and cosine of t. Clear? Okay, so you just put this vector here and acting at 1 0. So the answer which you are going to get, I am not calculating again, you can calculate it yourself. So you have to check it yourself. It is cosine t and sine t. Okay, so please check it yourself. Clear? Okay, so this is how you calculate this. Very, very simple. Okay, Now the thing is this: if I the question is which I want to pose is this question. Okay, you see, x prime equals to ax, x0 equals to x naught has a unique solution in terms of fundamental matrix, right? Solution in terms of fundamental matrix given by x of t, which is phi of t, fundamental matrix phi of t, phi inverse of 0 times x naught, right? That we know. Okay, so phi is a fundamental matrix. Okay, and you can show that this holds for all t in R. Okay, now the thing is, but again this theorem says that x prime equals to ax, x0 equals to x naught has this unique solution e power at times x naught. Okay, so is there a relation? So is there a relation of the fundamental matrix phi of a with exponential of a? What do you think? See, the thing is, you have to understand that in both the situations it is a unique solution, exactly same equation, and it passes through the same vector x naught in Rn, right? So therefore one can say that without putting much emphasis here, phi of t, phi inverse of 0 has to be e power at, no? It has to be e power at. There is no other option here. Okay, so you see, if there is, so this is another way of calculating e power a if you want. Okay, so if one can calculate, okay, we'll explore all these things in the future videos, but for now it is just for information. If one can calculate fundamental matrix, or if it is given, let's say, the fundamental matrix, then calculating exponential is easy. Exponential of a matrix is easy. Okay, now you have to understand, please remember this thing, this actually holds only when it is constant coefficient. Okay, variable coefficient equation, you can of course write it in terms of fundamental matrix, the solution, but you cannot have this thing. Clear? Okay, so phi t, phi inverse of 0 is nothing but e power a times t. Clear? Okay, so with this I am going to end this video.